On June 8, 2026, at 37 minutes past 7 in the morning local time, the southern coast of Mindanao took a hit it had not seen in the entire era of modern instruments. Magnitude 7.8. Depth 33 kilometers. The epicenter was 32 kilometers southwest of Masim, Sarangani province, right over one of the least studied subduction zones in the western Pacific Ocean. Write in the comments where you are watching us from. And we continue. In General Santos, a city with a population of over 700,000 people, buildings folded before the eyes of passers-by. A fast food restaurant collapsed at an intersection. Notre Dame of Dadiangas University lost a building in seconds. Police recorded 9 fatalities within the city limits alone in the first hours after the shock. And this was a Monday morning, the first day of the new school year. Schools were full. Children were sitting at their desks when the ground began to move. PHIVOLCS, the Philippine Institute of Volcanology and Seismology, issued a tsunami warning within a few minutes. It covered 9 coastal provinces, from Sarangani to Sulu, from Davao Occidental to Zamboanga. Waves of up to 1.5 meters were recorded on the coast. 2 people were swept out to sea near General Santos. The airport was closed. Flights were canceled until June 11th. More than 45,000 homes were damaged or destroyed across Mindanao. According to the NDRRMC, the death toll by June 12th reached 46. 688 injured. 38 people are still listed as missing. This is the strongest earthquake in the Philippines since 1990. But here is what makes this event not just major, but systemically significant. The June 8th earthquake was attributed to subduction along the Cotabato Trench, a deep-sea trench southwest of Mindanao, where the oceanic crust of the Celebes Sea plunges beneath the Philippine mobile belt. This is not just a fault. This is a generator, a structure that has shaped the seismic history of the southern Philippines over the past 100+ years. And this generator has a track record. In 1918, the Cotabato Trench produced a magnitude 8.3 earthquake, the strongest in the history of the archipelago. 58 years later, in 1976, the same trench generated a magnitude 8.0 shock. But it was not the earthquake that killed. It was what came 2 minutes after it. More on that a bit later. Right now, it is important to record something else. By June 12th, PHIVOLCS registered 3,860 aftershocks. 3 of them exceeded magnitude 6.0. The strongest was 6.7. This is not a dying down system. This is a system that redistributes stress. And the direction of this redistribution remains an open question for now. The data we are working with comes from open sources: USGS, PHIVOLCS, EMSC, NOAA, Temblor. Interpretations and connections between events are analytics, not scientific consensus. We do not make predictions. We read signals. And the signal that the Cotabato Trench has been sending over the past 5 months is worth reading carefully. The June 8th earthquake was not the first word from the Cotabato Trench this year. It was the last in a chain that began 5 months before the main shock, and which was recorded in real time. On January 19th, 2026, PHIVOLCS seismic stations on the southwestern coast of Mindanao began registering a series of shocks in the offshore zone of Sultan Kudarat province. The first events were weak, magnitude 1.4, 2.0, 2.3. Against the background of the usual microseismicity of an active subduction zone, this would not have attracted attention. But the shocks did not stop. They began to gain density. By January 22nd, PHIVOLCS reported 633 registered earthquakes. 197 were accurately localized. 30 of them were felt by residents of coastal villages. Magnitudes ranged from 1.4 to 5.2. The head of PHIVOLCS, Dr. Tedesito Bacolcol, confirmed that the generator of these events is the Cotabato Trench. The swarm did not stop. On January 28th, the strongest shock of the series occurred, magnitude 5.7. The epicenter was 55 kilometers southwest of the town of Calamansig, depth 19 kilometers. Hundreds of families in coastal areas of Sultan Kudarat began a preemptive evacuation. The provincial governor suspended work and school classes in 3 coastal municipalities, Calamansig, Lebak, and Palembang. PHIVOLCS did not issue a tsunami warning, but advised remaining prepared. By February 3rd, the total number of registered shocks reached 3,319. The peak of activity occurred on January 27th and 28th. 833 earthquakes in a single 24-hour period. 833. That is more than one event every 2 minutes, continuously, for 24 hours. By February 8th, the counter showed 3,570. Magnitudes ranged from 1.3 to 5.9. And then the swarm began to fade. The daily number of shocks dropped to dozens, then to single digits. By mid-February, PHIVOLCS recorded a steady decline. The agency noted that the swarm was gradually weakening, but added a caveat that is worth quoting verbatim. Strong earthquakes are still possible. Dr. Bacolcol was cautious in his wording. Earthquake swarms are not an automatic precursor to a larger event. They can reflect a gradual release of accumulated stress, a slow discharge rather than preparation for a rupture. But they can also be something else. And here is the problem. Scientists from PHIVOLCS noticed a detail that changes the context. The 2026 swarm did not happen out of nowhere. In 2025, a similar swarm was recorded in the same region, along the Cotabato Trench in the Palembang area. Both swarms were characterized by a reverse thrust mechanism, the type of movement expected in a subduction zone where one plate is forced under another. But a detailed analysis of focal mechanisms revealed a difference between them. The 2025 swarm showed rupture planes with an eastward dip and a northwest-southeast strike. The 2026 swarm shifted. The planes became oriented closer to a north-south direction. This is a technical detail, but for seismologists it means one thing. Stress was not just being released, it was migrating. And 4 months later, the trench responded with a magnitude 7.8. Stress migration along a subduction zone is not an abstraction. It is a physical process. And to understand why it matters right here, you need to understand what the structure that just went off actually is. The Cotabato Trench is a deep-sea trench about 300 kilometers long, stretching along the southwestern coast of Mindanao in the Celebes Sea. It marks the boundary where the oceanic lithosphere of the Celebes Sea plate plunges, subducts, beneath the Philippine Mobile Belt. The convergence rate according to geodetic data, is about 2.5 centimeters per year. This is not much on a human scale. But on a geological scale, it is continuous, unstoppable pressure. Every year, the plates move 25 millimeters closer. In a decade, by 1/4 of a meter. In a century, by 2.5 meters. And if the interface is locked, if the plates do not slide freely relative to each other but are stuck together, all this displacement does not disappear. It accumulates. Elastic deformation grows in the rock mass, like a compressed spring, until the strength of the material is exceeded. Then, a rupture occurs. And the longer the pause, the more energy is released at one time. Mindanao is located in one of the most tectonically complex zones on the planet. From the east, the Philippine Sea Plate subducts beneath the archipelago along the Philippine Trench. From the west and southwest, the Celebes Sea Plate plunges along the Cotabato Trench. The Philippine fault system passes through the entire island. 1,200 kilometers of strike-slip faults cutting through the Earth's crust. Add to this the Cotabato fault system, a network of left lateral strike-slip faults of northwest-southeast strike that compensate for the oblique component of convergence. Mindanao is not an island standing on a stable foundation. It is a crustal fragment pinched between converging plates, deforming from several directions simultaneously. That is why the seismic history of this region is so rich. According to PHIVOLCS data and the CEC historical catalog, at least 7 significant earthquakes with magnitudes ranging from 5.7 to 8.0 affected Sarangani and adjacent provinces between 1917 and 2023. The last destructive event before June of this year was magnitude 6.8 on November 17, 2023. Before it was magnitude 7.5 on March 6, 2002, with an epicenter southwest of Sultan Kudarat and a 3-meter tsunami. Even earlier, 1976. Even earlier, 1918. Each of these events is associated with the same structure, the Cotabato Trench. But here is what makes the current situation different from previous cycles. Geodetic measurements give a convergence rate of 2.5 centimeters per year under the condition of full plate coupling. Exactly 50 years have passed since the last major rupture on this segment of the trench, in 1976. If full locking of the interface is assumed, the accumulated slip deficit is about 125 centimeters. A meter and 25 centimeters of unrealized displacement locked in the rock under pressure. A magnitude 7.8 is capable of compensating for part of this deficit. But exactly which part depends on the rupture area and the amount of slip. And here begins the territory where the data stops giving a clear answer. The question of what proportion of the accumulated stress was compensated for by the June 8th rupture remains open. But the Cotabato Trench has its own chronology, which allows us to estimate the scale of what this system is capable of. And this chronology leaves no room for comfort. 1918. The Celebes Sea. Magnitude 8.3. The strongest earthquake in the history of the Philippine archipelago to this day. The rupture passed along the southern segment of the Cotabato Trench. Little data on casualties and destruction from that period has survived. The monitoring system was in its infancy, and coastal communities of southern Mindanao were practically not documented by the colonial administration. But the seismic record remained, and it recorded one thing. The trench is capable of generating events in the upper range of the eights. 58 years of silence. And then, August 17, 1976, 0 hours 11 minutes local time, Tuesday. Most of the Moro Gulf coast was asleep. Magnitude 8.0, depth 20 kilometers, epicenter in the Moro Gulf area, north of the 1918 rupture zone, closer to the eastern wing of the trench. This was a megathrust rupture, a release of stress at the boundary of the subducting plate. The shock was felt on all central islands of the archipelago and in the south of Luzon. But the earthquake was only the beginning. 2 to 5 minutes after the main shock, a wave came to the coast. Not just one, a series. A tsunami struck 700 kilometers of coastline along the Moro Gulf and the northern part of the Celebes Sea. Waves reached 9 meters in height. In the town of Labak, Sultan Kudarat province, water penetrated hundreds of meters inland. Pagadian, Cotabato City, Zamboanga. The entire coast took a hit simultaneously, in the dark, without warning. 85% of those who died were not killed by the earthquake. They were killed by water. According to official PHIVOLCS and NOAA data, between 5,000 and 8,000 people died or went missing. 10,000 were injured. 90,000 were left homeless. The 1976 tsunami became the deadliest in Philippine history. In terms of casualties, it exceeded even the consequences of Super Typhoon Haiyan in 2013. The reason for this scale of loss is a coincidence of factors, each of which, individually, would have been manageable. A shallow rupture focus, 20 kilometers. An underwater reverse thrust that displaced the water column. Nighttime. Most people were asleep. The absence of a tsunami warning system. And geography. The Moro Gulf acts as a natural concentrator of wave energy, focusing and amplifying the incoming wave. All this happened on the same trench that 5 days ago produced a magnitude 7.8. Researchers from PHIVOLCS and Temblor, in a publication dated May 15, 2026, 3 weeks before the earthquake, explicitly pointed out that the 2025 and 2026 swarms were occurring within the rupture zone of the 1976 earthquake. They asked a question that sounds different now than it did 3 weeks ago. Are these swarms an echo of that rupture, or a prelude to the next one? The question, posed by PHIVOLCS researchers 3 weeks before the main shock, received a partial answer on June 8th. The trench was not just echoing, it discharged. But the scale of this discharge, and what it means for neighboring segments, takes the analysis into a zone where certainty ends. A magnitude 7.8 is a major event. On the seismic energy scale, it is equivalent to approximately 1,400 kilotons in TNT equivalent. The rupture passed along the subduction interface of the Cotabato Trench with a reverse thrust mechanism at a depth of 33 kilometers. The USGS estimates the depth somewhat differently, 55.2 kilometers. The EMSC gives 45. The 22-kilometer discrepancy between two of the world's leading agencies is not a rounding error. It is a difference that affects the estimation of the rupture area, the slip amount, and critically, the calculation of stress transfer to neighboring structures. It is in stress transfer that the mechanism that turns a single earthquake into the start of a cascade is hidden. When a major rupture occurs on one segment of a fault zone, it redistributes elastic stresses in the surrounding crust. Sections that were close to their strength limit can receive an additional load and go off sooner than they would have without this shock. This is called Coulomb stress transfer. And it is this mechanism, according to a number of researchers, that links the largest events on the Cotabato Trench together. The 1918 rupture passed along the southern segment. The 1976 rupture passed along the northern one, with a shift to the east toward the Morro Gulf. The two events are separated by 58 years, but they occurred on adjacent segments of the exact same system. If the first rupture loaded the second segment with additional stress, and the geometry allows for this assumption, then 1976 was not a random coincidence, but a consequence. Now, 2026, the June 8th rupture is localized off the coast of Sarangani. According to preliminary data, the rupture zone is elongated southwest of Masim. The aftershock cloud, 3,860 shocks by June 12th, outlines the rupture area and shows which sections were involved. But it also shows which sections were not involved. The northern segment of the trench, the very one that devastated the Morro Gulf in 1976, did not participate in the current rupture. This does not mean it received a critical load. For such a statement, Coulomb transfer models are needed, which, at the time of recording this episode, have not yet been published. But it means that the stress accumulated on this segment, decades of convergence at 2.5 centimeters per year, remained unrealized. And here is a detail that forces a return to the chronology of 1976. The main shock of magnitude 8.0 was only the first blow. 12 hours later, a major aftershock followed, causing additional destruction. A series of aftershocks of magnitude 6.0 and higher continued for several more days. On June 8, 2026, mere hours after the main event, PHIVOLCS recorded an aftershock of magnitude 6.7. A parallel does not prove a repetition, but it establishes a precedent. The precedent on the Cotabato Trench is built around one system, one structure, one rupture line. But if you step back from southern Mindanao and look at the map of planetary seismicity over recent weeks, the picture expands, and not in the direction of calm. On June 8th, on the same calendar day the trench struck Sarangani, an event occurred on the opposite side of the planet that has no direct tectonic connection to the Philippines, but possesses its own anomalous significance. Magnitude 6.1, the Gulf of Mexico. The epicenter was 104 kilometers west-northwest of Mantua, Cuba. Depth, 26 kilometers. According to USGS data, this is the largest instrumentally recorded earthquake in the Gulf of Mexico since 1950. One of only 6 events of magnitude 5 and higher recorded in this water area over the past 76 years. USGS seismologist Paul Earle called the event unusual. It occurred inside a tectonic plate rather than at a boundary, in a zone where the last earthquake of comparable strength was recorded in 1880, 146 years ago. The shock was felt across Florida. In Miami, government buildings were evacuated. NWS Miami issued a notice stating there was no tsunami threat The very fact that such a notice was required for the Gulf of Mexico speaks to the scale of the event. The correlation in time with Mindanao does not mean a causal relationship, but two major events on the same day in two different tectonic contexts is a point worth noting on the map. It is not the only one. On April 20th, 2026, 7 weeks before the Mindanao earthquake, the Japan Trench generated a magnitude 7.4 to 7.5 event off the coast of Sanriku, Tohoku region. The JMA initially estimated the magnitude at 7.7, then adjusted it to 7.5. Depth, 35 kilometers. Mechanism, reverse thrust. Tsunami, 80 centimeters. 233 damaged buildings, 10 injured. This event was preceded by 162 foreshocks of magnitude 4.0 and higher, including a 6.8 shock in November 2025. The Japan Trench is a subduction zone of the Pacific Plate, the exact same trench that produced Tohoku 9.1 in 2011. Even earlier, on April 2nd, a magnitude 7.3 to 7.4 in North Maluku, Indonesia. Reverse thrust. Depth 35 kilometers. 1,378 aftershocks. 1 fatality, 4 injured. 3 events of magnitude 7.0 and higher in 10 weeks, all in the Western Pacific, all in subduction zones along the Pacific Ring of Fire. And against this background, the Sun. On June 3rd, 5 days before Mindanao, active region AR4455 produced an X1.0 class flare, causing an R3 level radio blackout on the day side of Earth. The monthly sunspot number in May reached 125.69. Solar cycle 25 continues to hold near its predicted maximum. No agency records a proven link between solar activity and seismicity, but both processes are occurring simultaneously, and both are in a phase of increased intensity. The simultaneity of events at different ends of the planet does not prove a systemic link, but it outlines a contour that deserves to be seen as a whole, not as a set of separate points, but as a state. Here is what we have at the moment. The Cotabato Trench, a structure capable of generating earthquakes in the upper range of the Eights, has gone through a sequence that can be described in 3 phases. First, a double swarm stretching over 2 years, 2025 and 2026, with a combined number of shocks numbering in the thousands and a migration of focal mechanisms indicating a redistribution of stresses within the subduction zone. Second, the main rupture of magnitude 7.8 on June 8th, localized on the southern segment off the coast of Sarangani. Third, an ongoing aftershock sequence, nearly 4,000 shocks in 5 days, with 3 events above 6, including a 6.7 in the first hours. Each of these phases individually fits into the standard model of a seismic cycle. Swarm activity in subduction zones is normal. A major earthquake on a trench is expected. An aftershock sequence after magnitude 7.8 is predictable. But this sequence is unfolding on a system whose history contains a specific precedent, a transition from a major event on one segment to a catastrophic event on an adjacent one. 1918, south. 1976, north. Between them, 58 years and Coulomb stress transfer, which likely loaded the northern segment to a critical threshold. Exactly 50 years have passed since 1976. At a convergence rate of 2.5 centimeters per year, and assuming significant locking at the interface, The slip deficit on the northern segment could be on the order of 1 meter to 1.25 meters. The June 8th event is localized further south. The northern segment, the 76 rupture zone, did not participate in the current event. This is not a prediction. This is arithmetic. And arithmetic does not say when the next rupture will occur. It says that the material for it exists. Now let us expand the frame. 3 major subduction earthquakes in the Western Pacific in 10 weeks. North Maluku, Sanriku, Mindanao. An anomalous intraplate event in the Gulf of Mexico with no analogs in a century and a half. Solar cycle 25 holding near its peak of activity with regular X-class flares. None of these elements on its own is a catastrophic signal. The planet generates an average of 15 to 20 events of magnitude 7.0 and higher annually. Solar maxima happen every 11 years. Intraplate earthquakes are rare but documented. But when these elements coincide in time, when subduction zones of the same belt activate within a narrow window, when a trench with a history of cascade destruction emerges from decades of accumulation, the combination gains weight that exceeds the sum of its parts. And in this combination, one question remains to which science does not yet have an answer. Is the magnitude 7.8 on June 8th an event or a signal before an event? This question is not rhetorical. It stands in the working documents of PHIVOLCS. It is implied in the Temblor publication of May 15th, the very one that came out 3 weeks before the trench confirmed that swarm activity was not a harmless release of pressure. And it remains unanswered at the time of recording this episode because data for an unambiguous interpretation is not yet sufficient. Here is what is known. The aftershock sequence continues. By June 12th, the 4th day after the main shock, PHIVOLCS recorded 3,860 aftershocks. 23 of them were felt by residents of Sarangani, South Cotabato, Davao Occidental. The system has not transitioned into a decay mode where the number and magnitude of aftershocks monotonically decrease according to Omori's law. It generates bursts. It redistributes. Coulomb stress transfer models for the June 8th event are not published at the time of recording. This means that the question of the load on the northern segment of the trench, the segment responsible for the 1976 catastrophe, remains in a zone of uncertainty. No agency has issued a warning about an increased probability of a repeated major event. But monitoring continues, and PHIVOLCS wordings remain cautious. Aftershocks may persist for days and weeks, and some of them may be felt. For up-to-date safety information, residents of affected regions should turn to PHIVOLCS, NDRRMC, and local disaster risk management agencies. And now, one step back. On the morning of June 8th, at 37 minutes past 7, children in southern Mindanao were sitting at their desks. It was the first day of the 2026-27 school year. At Mahayag Elementary School, teachers and students ended up on the floor when the walls began to move. A canopy collapsed a few seconds later. No one at that school died, but 8,642 schools across Mindanao suffered damage. The last time the Cotabato Trench produced a comparable strike, it came at night when people were asleep. And after it came the water. On June 8th, water came too. Waves of up to 1.5 meters on the coast of Sarangani in Sultan Kudarat. 1.5 meters is a warning, not a catastrophe. In 1976, the waves were 9 meters. The difference between 1.5 and 9 meters is the difference between a magnitude 7.8 and a magnitude 8.0 on a shallow megathrust rupture with optimal geometry for tsunami generation. The difference is 0.2 of a magnitude, 3 times more energy, and thousands of lives. The Cotabato Trench is currently in a state that seismologists call post-seismic relaxation. The crust is readjusting. Stresses are migrating. Stations record every impulse. What happens next depends on the physics unfolding at a depth of 30 kilometers beneath the Celebes Sea. Right now, while you are listening to this, the trench is not finished.